Hello, welcome to another module in this massive open online course. Alright, so we are looking at IIR filter structures, and in this one we will start looking at another filter structure, that is the transpose form. Okay, so we are looking at IIR IIR filter structures, and as part of that we are looking at the transpose structure, or let us call this the transpose form. And the transpose form can be described as follows. Now, again consider our Hz, the transfer function equals Yz divided by Xz, let us say that is given as follows, equals, let us say, similar to what we have considered before, Pz divided by Dz. So, this implies Yz equals Xz, and now previously we had written it as cascade of first Pz followed by 1 over Dz. Now, let us write it as cascade of 1 over Dz followed by Pz. Okay, so, and we will call this Xz over Dz, we will term this as Wz, and Wz is later on, and therefore, I can also write this as Wz times Pz. Okay. And therefore, if you look at this, we have Xz equals Wz times Dz equals Wz times 1 plus d1z plus d2z minus 2 plus d3z minus 3, which implies I can now write, converting it into the time domain, this implies that, alright, I have x of n minus d1 w n minus 1 minus d2 w n minus 2 minus d3 w n minus 3. This quantity equals your w n. Okay. Therefore, I can write this, alright. So, we have developed this relation, that is x n minus d1 w n minus 1 minus d2 w n minus 2 minus d3 w n minus 3 equals w n. Okay, and this is the first stage of the cascade. Okay. So, I can write this as, I can represent this as x n, an adder that gives rise to w n, and w n is in turn being fed as follows. So, I will have z inverse, that is a delay, this is w n. Okay. We have here, we will have another adder, and then of course, this has to be multiplied by minus d1, okay, and we will have here we will have another delay element z inverse, okay, and we will have another adder, another gain, minus d2, okay, and finally, we will have another element here. This is an adder, this is a delay, and here of course, there will be another gain that will be minus d3, and this will be again all right, this is minus d3, and therefore, now if you see, and this Wn, we will complete this later, is being passed forward. So, now if you see this here, this element at this point we have minus d1 Wn, and at this point we have minus d2 Wn, and at this point we have minus d3 Wn, and you can see here I have minus d3 Wn minus 1. At this point I have minus d3 Wn minus 1 further delayed. So, that will be minus d3 Wn minus 2 minus d2 Wn minus 1, and at this point finally I will have minus d3 Wn minus 3 minus d2 Wn minus 2 minus d1 Wn minus 1 added to xn, that produces your yn. Okay. So, that is basically the first part. So, this part is implementing your Wz equals xz over tz. Okay. So, now we have this quantity Wn, all right, and now from Wn we have to generate yn, all right. So, and we know that Wz into Pz is yz. Okay. So, using that, using this system we generate that leads to the output yz. Okay. So, we have yz equals Wz times Pz, which is Wz times that will be P naught plus P1 z inverse plus P2 z minus 2 plus P3 z minus 3, and that will be, and this implies basically that yn equals simply P naught Wn plus P1 Wn minus 1 plus P2 Wn minus 2 plus P3 Wn minus 3, and that is the forward path. And now you can see Wn, send it through gain P naught, okay. So, adder, that gives me Wyn. Now, this I have to also send through gain P1, and this will be delay z inverse, all right, and that will be that again you have another adder here, okay, and that will give you this is P1 Wn, and now I will send that through another gain, that is P2, and this is well another delay over here, and finally you send it through another gain stage, that is and another delay. So, that will give me, the gain is P3, and so what you have here is basically you can see, let me just mark this, at this stage you have P1 Wn, at this stage you have P2 Wn, and at this stage you have P3 Wn. Here at this point you have P3 Wn minus 1, at this point you have P3, because it is passing through two delays, P3 Wn minus 2 plus P1 W n minus 1, and at this stage you have P3 W n minus 3 plus I am sorry, this is P2 W n minus 1, alright. So, plus P2 W n minus 2 plus P1 W n minus 1, okay. And so, what you have over here will be, and now you are adding this to P naught W n, P naught W n, so that gives you Y n. So, that basically completes, and this part basically implements the W z into P z. So, this is basically your cascade of first 1 over d z with W z. So, you can just write this as cascade of 1 over d z followed by P z, okay. And now once again, so remember, similar to what we did for the direct form, what we want to do here is we want to now interchange these two branches, and once we interchange these two branches, we can see that the resulting delays, and in this case in fact even the adders can be combined for both the branches. So, once you combine them, now then you will get the representation with the minimum number of delays and adders. So, what we are going to do again here is we will interchange branches and merge the common delays and adders, okay. So, what we will do is we will interchange and we will merge the common we will interchange, and this yields structure below. This yields the structure that is shown below, which is basically and you can derive this. I am not going to explicitly show the steps, but you can do this as an exercise. So, this will give you P naught, this is the element gain, this will give you Y n, okay, and here you will have a delay Z inverse, all right, and another adder, and from this you will have minus D1, and here you will have minus D2 and this one is minus D3. There will also be one delay, okay, and I am sorry, this is P1 and this will be P2, okay. Remember, you are interchanging the branches, so this will be minus D2 okay, and finally you will have one more and this will be gain will be P3 and this gain is minus D3, and what you have over here is basically this is termed. So, this is the alternative representation, this is termed as the direct form. So, previously what we this is termed as the direct form 2 for the transpose. So, what we have over here is the direct form 1, this is termed as the previous one is termed as direct form 1 transpose. We have seen previously direct form 1 and direct form 2. So, this is the direct form transpose. Okay. So, this is the transpose structure that is denoted by this T in the subscript, and what we have over here is this is your direct form 2 transpose. And this T in the subscript, this denotes the transpose. Okay. And what we have is basically, you can now see that we have the minimum number of delays, because previously in the direct form 1 transpose we had you can see we basically have 6 delays and we have 7 adders, if I can count correctly. So, this has not 6 delays, this is not an adder, you do not need this actually. So, you just join this here, and what you have is basically, you can see you have 6 delays and 3 adders. So, this has 6 delays plus 3 adders, 3 adder elements. But if you look at the transpose, if you look at the direct form 2 transpose, that has only 3 delays plus it has only 4 adders. So, the direct form 2 transpose has fewer number of delays, similar to what you saw in the direct form 2, correct. This is the transpose, and this has fewer alright. So, in comparison to the direct form 1 transpose, this has fewer delays, that is from 6 the number of delays is reduced to 3. In addition, the number of adders has also significantly decreased from 6 to 4 adders. So, this is the minimal representation in terms of the number of delays plus the number of adders. Okay. So, this results in the minimum number of delays this has the minimum number of delays and adders. Okay. So, that is the direct form. So, that describes basically the direct form 2 transpose. Alright. So, in this module what we have seen is we have looked at the direct form 2, the direct form 1 its transpose structure, and also the direct form 2 its transpose structure, and we have seen that the direct form 2 transpose results in the minimum number of adders and delays. So, let us stop this module here and continue in the subsequent. Thank you very much.